So welcome to the lecture on application of MATLAB in automatic control. So in this lecture we will discuss how to plot or how to find the transfer function, poles, zeros and responses of the system, of any system using MATLAB. So I think most of you will be familiar with the MATLAB. So MATLAB is a mathematical tool that is used to modeling, analysis and design, in modeling, analysis and design. So we can use matrix algebra, we can use differential equations, we can plot any function. So there is wide application. So how we can use this in automatic control? So what the theories we have already discussed in the last lectures, and we have discussed some numerical problems also in those sections. Now when we want to solve those problems in MATLAB or similar problems, how can we do? So in MATLAB we discussed about transfer, we will discuss about transfer function. So how we can obtain transfer function, how we can obtain poles, how we can obtain zero, and the response, if there is some step response, impulse response and so on for a system. So here let's take the first problem that we can see, that create the following transfer function using MATLAB and then convert from polynomial form to factored form. So here this is the transfer function. We know this is the transfer function, s plus 2 by s square plus 3s plus 1. And factored form means if there is some factor, because this is the square in the denominator, this numerator is already factored. Here in denominator there are two roots, so we can factor into 2. So that is factored form. So how can so of course we can do this manually, but for example if we want to do manually, we can have like this is our HS and this is our input and this is our output. So here HS is given as s plus 2 upon s square plus 3s plus 1. So we can factor this by finding the roots. So s equal to minus 3 plus minus under root b square, so 3 square minus 4 ac upon 2. So we can write minus 3 by 2 plus minus, so 9 minus 4, so this is root 5 by 2. So we will have the, if we want to, so we have this root minus 1.5 plus root 5 by 2 and minus 1.5 minus root 5 by 2. So here if we want to use the MATLAB, so we have to open. So this is the MATLAB command window. We can write here the commands. So here if we want to find the transfer function, we can use a command that is tf command we can use, and that is we can say tf numerator and denominator. So this is the command. So tf num den. Now numerator we have to write. So here numerator is s plus 2. So highest power of s is 1, its coefficient is 1, and then the next power coefficient, that is 2. So here we have to write 1, 2, that is numerator, and denominator so we have denominator s square plus 3s plus 1. So highest power of s is 2, its coefficient is 1, then next lower power is s, and that is coefficient is 3, and then s0, so it is 1. So we have to write 1, 3, 1. So here let's say this is a system. So of course this command, when we write in MATLAB we have to first define these variables. So num, then here we can write, then only we can use, let's say sys equal to tf num comma den. So this is our, we will get the sys is the transfer function that has the numerator this and denominator 1, 3, 1. So we see if we write this here. So let's write num equal to 1 space 2, then so we already define, we can see here we have defined num here in workspace, we have defined num 1, 2. So here if we want to see here what is num, so we see num is 1, 2. So now den, we define den equal to 1, 3, 1. So this is den, and we can see here in the work space there is a den variable created that has elements 1, 3 and 1. So if we write den and we put enter, we will find these the elements of den. So it is, we define a vector or matrix. So this is den. Now we have to find the transfer function. So these are, we have to find sys. So sys means we are giving some name to system. System equal to tf, and we use this command num den. So here, so there should not be we have done some mistake here. So here we have unbalanced or unexpected parentheses. So we should not use this, we have to use the small bracket. So sys equal to tf, so this one, because here you see we are getting tf small parenthesis num den. So here num den, so we have now this, and then we can use this semicolon. So now we have obtained this sys. You can see we have obtained sys, that is 1 by 1 by 1 matrix, you can say, or vector. So here we have one by one sys. Now if we want to know what is this sys, so we enter, and you can say we can find this transfer function s plus 2 s square plus 3s plus 1. So we have found a continuous time transfer function. So this is the continuous transfer function. Now we want to obtain the factored form. So we want to obtain this factored form as I described. So we can write, so that is called ZPK. So Z means 0, P means pole, and K means gain. So if this transfer function can be written in a form like, let's say s plus z1 by s plus p1 and s plus p2, and if there is some gain, if it is 1, okay, if there is some gain 5, 10, 100, so that should be here. So this is a factored form. So now we say 0, that is z, poles and gain. So we call it ZPK. So here we have to find this sys underscore ZPK equal to. So now this sys is the now in the transfer function. This is a transfer function form. We want to convert this in this form, factored form. So we use this sys for the command ZPK. Sys means this ZPK command will convert this sys, that is a transfer function, to 0, pole and gain form. That is that shown on here. So if we put this, so we are getting here, you can see here s plus 2 upon s plus 2.618 and s plus 0.382. So this is root 5, that is about something 2 point something by 2, so it is about 1 point something, and if you deduce this one, it is about minus point, so less than minus 0.5. So that is minus, here we can see 0.382 we are getting, and the other is we are adding here 1 point something, so it is minus 2.6. So here we have s plus 2.618. So when we do the factored form, now we obtain this factored form s plus 2 upon s plus 2.6 so this hs we represented in factored form. So now from seeing this factored form, we can tell that what is 0. So 0 is at s equal to minus 2. Poles are at s equal to minus 0.382 and minus 2.618. And then we know that gain here is 1. So gain k equal to 1. So by seeing the factored form, we can know these informations. Now here we can also know about the poles. So if we write pole sys, so you can see that by giving this command pole, we can pole sys. So sys is the transfer function, and if we give the pole command, we can directly get the poles, that is minus 2.618 and minus 0.382. So we can get the poles, either we go in the factored form and we can find the poles, or we can give this command pole sys. We can also give a command that is called 0 sys. So we get here -2. So here the 0 is -2. Second thing is that we can apply this same thing on the ZPK system also. So if we say pole ZPK sys underscore ZPK, we can again get the pole. So we can either any form, either the transfer function form or factored form. If we give the pole command, we will get the poles, and if we give the 0 command, we can get the zeros. So that is -2. Now one more thing is that we have this transfer function, and we know that we are here to get the poles. We are calculating the roots of this polynomial. So we can also get this using the roots of the polynomial. So here we have a polynomial s square plus 3s plus 1. So if we don't know that how to find, we have to see for the help. So here is the help, and in the help we can go to the documentation. So in the documentation, if I want to find the roots, we can search for the roots and enter. Here is the roots, so polynomial roots. We can go in the command how to use this. So it's written all these helps, that polynomial roots. The roots function solves polynomial equation of the form p1 xn plus pnx plus pn plus 1 equal to 0. That polynomial equations contain a single variable with non-negative exponents. To find the roots of the types of equation, use f0. Now here the syntax is r equal to roots p. Now roots p, we can see here the example that if we have this equation 3x square minus 2x minus 4 equal to 0, 3x square minus 2x minus 4 equal to 0, we have to define the polynomial p equal to, again, the coefficients of the highest power, that is 3, then the next lower power of x, that is -2, then the next lower power, that is -4. Suppose if there is no x here, this part is not here, we have to put here in place of -2 we have to put 0. We can't leave this. So 3 minus 2 minus 4, and then we say r equal to roots of p, and we will find the roots. So let's apply this here. So we have, this is the polynomial s square plus 3s plus 1, and we have this polynomial 1 3 1, and we can find here, if we say r equal to roots, so we first define the polynomial p equal to, we can see how we can define. So p equal to 1 3 1. So we have defined a polynomial, so we can see here p equal to 1 3 1. Now we say r equal to roots and p. So so we have got the roots, and if we say r, so you can see here we have got the roots minus 2.618 and minus 0.382. So they are the poles of the system, because the poles are nothing but the roots of the denominator or characteristic equation, and the roots will give us also the poles. So we see how many ways we can find the poles of the system of a transfer function. So here now we want to go for the second problem, and we want to clean this screen, because so we say CLC, so we have cleaned this command window. If you also want to clean this workspace, we can say clear all, so it will clear this workspace, and CLC, so it will clear the window. Now we want to go for the next problem here. So this problem number 2, we want to create the following transfer function by assigning a variable as a variable of the transfer function. So here this is the transfer function in factored form, and then we want to convert this transfer function from factored form to polynomial form. So the transfer function, this is the ZPK form. First we have that is factored form, and we have to define a variable s, and then we have to write this in factored form, and then to convert in the polynomial form. So we can go in the MATLAB. So here we can define here a variable s, that is ZPK s. So this is the s is the variable of this model ZPK, and then we type this system sys equal to, so s minus 2 into s plus 1 upon s plus 3 square into s minus 5. So here we have defined sys, that is s minus 2, s plus 1, s plus 3 square, s minus 5. Now we define the variable s, the variable of the transfer function. So s equal to tf s. So now this is the s is the variable of the transfer function. Earlier it was the variable of the zero pole gain model. Now we have to write sys, let's say sys 2 equal to, so we can also bring this, so sys equal to s minus 2 into s plus 1. So this, now if we do this, we will get the transfer function. So we have obtained the from factored form to polynomial form. Earlier form was factored form, and here we have got the polynomial form of the transfer function. So now we come to the so let's say CLC command. So we clear the screen and clear all. So we clear all. Now we come to the next problem, that is problem number 3. Find the poles and zeros of the following transfer function and plot them in the complex plane. So we have HS equal to s plus 4 upon s plus 1 square and s plus 3. So we have to find the poles and zeros. So we go in the MATLAB. So here we have, we can define the zero z, that is z, a variable that is has a 0, that is minus 4. So this is a z is a variable that is 0, and then p is a variable that is So here we are writing that it is s plus 4 upon s plus 1 square, s plus 1 square, s plus 3. So this is our HS, the transfer function. Now here we have ZPK model. So we write Z as a polynomial. So it contains, no, here we are already writing this. The zeros is -4, the P is -1, -1, -3. So there are 3 poles at -1, -1, -3. So we can write cis equal to ZPK Z, P and K. So we can use the ZPK model to find the system. So we have not defined the K. K is the gain, which is 1. Now we can again use this command and we will find this transfer function that is in the ZPK model or factored form. So now we can find pole. So as we already know the poles and zeros, but once we can create this in this form, we can find the pole of system, that is -1, -3, -3 and 0 of the system. So now we want to plot this PZ map system. So we want to plot these poles and zeros. So we can see here we have obtained these poles. So here we can see here this is imaginary axis, this is real axis, and there is a pole. There are 2 poles at -1, so they are overlapped here, and here is 1 pole at -3, and there is a 0 at -4. So this is 1 0. We can see here a 0 at -4. This is a pole at -3, and here we have 2 poles at this location. So this. Now we come to the next problem. Now we have the transfer function of a system. We have to find the poles and zeros of the system, and then we have to find the impulse response, step response, and the response with some arbitrary input signal, that is 2 cos 1.6t in the interval of 0 to 10. So we have this system, that is transfer function GS equal to s square plus 2s plus 1 upon s cube plus 4s square plus 8s plus 6. So this is our system, and here we have to find the response of impulse and step response of the system. So here let's go in the MATLAB. So now we have to first find the system. So system, we can directly write system equal to TF, and we know that numerator comma denominator. So numerator here is, we have s square plus 2s plus 1. So s square coefficient is 1, then 2s, and then 1. So this is numerator comma denominator. So denominator is s cube, so 1, then 4s square, so it is 4, then 8s, so 8, and then 6, so 6. And so this is the system, and we enter, we will get cis s square plus 2s plus 1, s cube plus 4s square plus 8s plus 6. Now we have to find poles. So we know that P equal to pole sys. So we have got the poles. Now we have to find the zeros. So Z equal to 0 sys. We have obtained the 0, that is -1 -1. So there are two zeros at the same location. Now we define the time between 0 to 10. So in MATLAB we have to give some time interval and discretize the time. So we time equal to 0 to 10, 0 to 10, but we have to give the increment interval, that is 0.1. So 0 to 0.1 to 10. So this is the time we have given. So there is a vector time t we have already created. Now we define, because we have to find also the last part, the arbitrary input u equal to 2 cos 1.6 t. So we have 2 into cos 1.6 into t. So now we can see we have created input u. Now you can see what is t. So t is the time. You can see here we are starting time from 0. We have given the increment 0.1 till 10 seconds. So 0, 0.1, then increment of 0.1 will make it 0.2. So we are giving the values of time 0, then 0.1, 0.2, 0.3 and so on till 10 seconds. So here you can say 9.9 and then 10. Now u is defined for each of these points with the function 2 cos 1.6 t. So u is equal to, again it has calculated the values of u. So you can see here when t equal to 0 u is 2, and that you can see there is 2 cos 1.6 t, and t equal to 0, so cos 0 is 1. So we will get maximum value 2, and then when t will increase, the value will increase and vary, and then we at 10 we are going to get this -1 point. So we have got an input of like this. So we have the time t, okay, and we have this cosine function. So this is 2 and varying till here we have time t equal to 10 seconds, and here t equal to 0. So this is our input. However, we have to find the impulse input first, or step input. So let's first find impulse. So we just write impulse and we say system sys. So we have defined the system sys. So impulse sys, we obtain here the impulse response. So we are giving some impulse and we are getting the response. Now we give the step. So step and sys. So we will get sys. So step response. So we are giving the step input and we are giving the step. So here is some step response of the system. Then we use the command lsim sys u t. So this is lsim is doing the simulation under some arbitrary input u. So this is the input and time relationship ut, and this is a system. So we do lsim. So we will get the input. So you see we are getting, here is the input, that is 2 cos 1.60, and this is the output we are getting here, the output. So here it shows that the system has some this output that is below the input. So these are the some plot the response of the following transfer functions. So these are the transfer functions: 9 upon s square plus 9x 9s plus 9. So let's continue this in the next lecture. So let's stop and see you in the next lecture. Thank you.